Thanks. At the outset, I would like to thank the organizers for inviting me to present in this very nice meeting. And also, I would like to congratulate both Chandan and HRK for their birthday, and I wish them many more years of fruitful science and healthy life. Okay, so it is quite appropriate that I am actually giving this talk, this talk over here. So I actually work with Chandan and Praval and Ajay Sood. So that was not exactly on these sort of topics. So this was, it was about properties of confined water in carbon nanotubes. So keeping with the theme of the group at that time, so there were lots of cross interactions, and so as a result of that, I have been sort of slowly approaching into this area of dynamics of liquids in these glassy and amorphous systems, and this is what I have been doing for the past few years, and I will be trying to talk to you about this. So there are lots of experts in this audience, and I would like to have a very honest feedback about these sort of problems which I'm thinking. Anyway, so yeah, so it's essentially about liquids and how single molecules actually translocate in liquids, move in liquids. So this is a very old problem, and so I'm trying to, so essential feature of this single molecule dynamics in liquids is actually governed by this fact that liquids possess short-range positional order. So this actually induces some amount of caging. So each molecule in a liquid is locally caged in a set of its immediate neighbors. And then what happens as a result of thermal fluctuations, these cages can break intermittently, and these molecules can move, break away from these cages, and then go and be trapped in another cage. And sort of this sequence of events keeps on happening. As a result of this, as a result of such several number of cage breaking and events, so it can actually then move by long distances and eventually reach its diffusive regime. So for several of these liquids, say the supercooled liquids, or some, I will actually discuss some deep eutectic mixtures and some ionic liquids, the time taken to reach this diffusive regime is pretty long, and there are lots of intermittencies happening, and one should actually look into whole of this details of the dynamics in the intermediate time period, because that's important. Anyway, so this is actually true for both translation and rotation. I will discuss in details two examples, one where I will talk about translations in liquid crystalline molecules, and then in the second part, I will talk about the rotation in a series of liquids, starting with supercooled water and then deep eutectic mixtures. So for these liquids, they are actually, the microscopic motion is actually governed by the strong hydrogen bonds. Okay. So the first example which I will talk about is the motion of liquid crystals, single molecule dynamics of liquid crystals in this Smectic phase. So this Smectic phase is a sort of stacked of layers of molecules which are orientationally ordered, and it also has a one-dimensional periodicity. So here it's the free energy surface. So what happens is that the molecules like to sit in the at the center of these Smectic layers, and with an orientation where it is sort of parallel to the director. So the director is the average direction along which these molecules are oriented. So now, that is this position. This is one of the stable minima of these things. Now the point is that we are trying to address the motion of these, how these molecules actually move from this one of these minima to its the next layer, basically. So it appears that for these molecules, which are sort of flexible molecules, which has a stiff core, and there are these flexible tails, which are alkyl tails. So there are two pathways actually. One is a direct pathway, which is termed as a straight translocation. The molecule actually translocates from this layer to the next layer without changing its orientation. And then another competing pathway where the molecule actually moves from here to the interlayer space, and then it actually is oriented in a perpendicular to the director. And it lingers there for some time, and then it moves to the next layer, next stable minimum. This is termed as the parking lot mechanism. So if you look into a typical trajectory of these molecules, And so you can see lots of these waiting times and these sort of transitions between layers of these molecules. And these red lines across here, they are the positions of the smectic layers, the centers of the smectic layers. So the typical, again, the typical free energy landscape of the barriers, which are associated with around 5 to 10 kV. Okay, the second problem, which I will talk about in some detail, is about the sort of rotation in hydrogen bonded fluids. So this is a prototypical example which I will discuss about water, but it seems that we have been able to work out that this similar sort of mechanism also applies for a huge class of hydrogen bonded liquids like deep eutectic mixtures, ionic liquids. So the basic mechanism is the same. So the main issue here is that these water molecules, you are trying to track the rotation of these water molecules. And initially the view which was held was that this is sort of diffusive at all time scales. But in some recent works, it's about in 2006, J.T. Hines, there appeared a paper in Science which actually showed that this is actually not true. So the water, the rotational dynamics of water comprises of diffusive motion and also primarily by large amplitude angular jumps. So what is plotted over here, you take a typical water molecule in a simulation box and there you actually try to plot the angular position vector of an OH vector, any OH vector arbitrarily, and there you actually see regions where it is sort of localized, and then there are these regions where it jumps from one local minima to another. So there is another interesting, fascinating aspect about this. So this rotation is actually associated with some amount of translation amongst these nearest neighbors. So what is happening is that one of this rotating water molecule actually is breaking a hydrogen bond with one of its neighbors and rotating and simultaneously forming another hydrogen bond with another neighbor. So as a result of this initial neighbor is actually moving away from its first solvation shell to the second one, and its final neighbor is actually coming in from the second solvation shell to the first one. So there is a significant amount of microscopic rotation translation coupling. And the point is that there is no such microscopic measure of this rotation translation coupling. I think this microscopic rotation translation coupling can be a very nice measure of actually understanding the way various liquids move and actually categorizing these liquids. Anyway, so now comes the basic plan and motivation. So what I will be discussing is sort of trying to detection. So first is the detection of these basic dynamical events from, I'm doing MD simulations. So from these MD trajectories, I would like to detect these basic dynamical mechanisms and then apply this formalism of continuous time random walk to relate the properties of these microscopic dynamical events to macroscopic transport. So when one thinks of macroscopic transport, the first thing which is come is the diffusion constant, which is an ensemble average quantities, which is related to the slope of the mean square displacement. So now, as liquids are sort of supercooled, I will discuss one example of supercooled liquid at the end of this talk, where I talk about supercooled water. So the dynamics is actually dominated by the fluctuations and not the mean or the diffusion constant. So the full range of statistical properties of these dynamical events, full range of temporal statistics is one has to understand. And then they are sort of related to these typical measures of these dynamical heterogeneities, which are sort of ubiquitous in these amorphous liquids. So a little bit about introduction about dynamical heterogeneities, which might be redundant to this audience, but anyway. So it is sort of observed in various circumstances in colloidal fluids, foams, gels, fiber networks, etc. So what is one trying to say? If one is trying to look at these single molecule trajectories and plotting the mean square displacement of the several single molecule trajectories, it actually shows a wide variation. And if you compute the mean of all these trajectories, you see a red line over here. But the point is that the trajectories are actually spread out much beyond this sort of mean line. So So what is a typical measure is that you try to calculate the Van Hoff function, which is basically what is the probability that the molecule moves a distance r in a given time t. So at high temperature liquids, this Van Hoff function is a Gaussian, but as you supercool the liquids, what happens is that this Gaussian has broader exponential tails. So this emergence of this exponential tails has been explained by continuous time random walk, and this work by Pinaki and also Walter is here. So this is a Conmat journal Physics Conmat paper, and there is also a PRL paper, 2007. Anyway, so the next concept which I will sort of try to touch is that this diffusion is obviously Fichtean, but this is non-Gaussian. Anyway, so this came up in this Steve Granick's paper in Nature Materials, and there he showed that it is actually possible to deconvolute this Van Hoff function into several Gaussians and show that you can obtain a bimodal density distribution, which actually shows that there is that the slow particles and fast particles sort of coexist in this liquid under these conditions. Okay. So next, a little bit about this continuous time random walk. So what one is trying to find is that these locate the sort of cage regime and sort of the jump regimes. And once one locates them, so these molecules can sort of jump from one side to the next one at random times. So, and these times are actually drawn from a waiting or a residence time distribution. That is one quantity which takes care of all the temporal characteristics of the motion, and another quantity which is the distribution of the jump amplitudes. So these are, I'll be discussing these off lattice systems. So there will be several jump amplitudes and a distribution of them. So that is encoded in this jump length distribution. So the conditions under which a continuous time random walk description is viable is that there should be no correlations between jump amplitudes and the waiting times, which we will see that this sort of applies in the liquid crystalline problem. And another thing is that the typical waiting time, sorry, I have this inequality wrong. This should be, the typical waiting time should be much greater than the time to jump from one local minima to another. Sorry. Anyway, so with that, let's move to the first problem. So I will be discussing this dynamics in the Smectic phase. So this is a slight introduction about the various liquid crystalline phases. At the highest temperature, with these anisotropic interactions, you have this isotropic phase where there is no either positional or orientational order. So as you cool down, you first encounter the nematic phase, where you have an average orientational order, and then if you cool the system further, you have this Smectic phases emerge, where you have an average director where the molecule points, and also a one-dimensional translational periodicity in this direction. So I'll be talking about the Smectic A phase. So the Smectic phase you can think of as sort of 2D liquids which are stacked on top of each other. Okay, so I have already talked about a little bit about this. So this is actually done on this liquid crystalline molecule, which is a sort of real molecule, which is a variant of this azobenzene. So this has a central core, which is a very stiff core, which is the azobenzene, and with this alkyl tails. So here I will talk about the basic translocation mechanisms are these two, where one is the straight, where the molecules actually move from one top layer to the bottom via this straight mechanism, and the second mechanism is where they actually linger in the interlayer space oriented perpendicularly for some time and then move. So this is goes by the name of parking lot translocation processes. So this typical trajectories, you will have a lot of these periods which are periods of waiting in this thing, and then there are these periods of jumps where these translocations are happening. Now you can from these trajectories you can always find out at what times each molecule is jumping from one layer to another, and then what we do after we find all these translocation times, we actually go to each of them and try to figure out in which category this sort of translocation forms. So there are now some cutoffs on these angles which these molecules make with the director. So it can be a straight translocation or a parking lot translocation. Okay, so the basic features of the dynamics in the Smectic phase is encoded over here. So you have a residence time distribution in the Smectic layers, which is exponential over here, and you have the jump length distribution. So the molecules can either jump from one layer to the next in the front direction or the backward direction. So these peaks appear at the layer spacing, and this shows that I have plotted the residence times and the jump length, which is follows this residence time, and you can actually see that there is no sort of correlation between residence times and jump lengths, which actually tells you that this is a good candidate for a continuous time random walk distribution. Okay, so now once you have actually identified all these translocation processes, so what you can do is that you can calculate and plot as a function of time the total number of translocation processes. So you take some time origin and some later time. Between these two times, for each molecule, you can calculate the average total number of processes. Also, you can calculate the average number of individual processes. And obviously, this is true for each given molecule, that the total number of processes is just a sum of the number of straight translocations and number of particle translocations. Okay. So now, if you plot these things as a function of time, at long times, they are sort of linear in time, and they go as tau by some residual characteristics times. So now the total n total is designated by this t by some tau effective, and this n straight has a t by tau straight, and similarly for this. Now, since the total number of jumps is sum of the number of straight and the parking lot jumps, this relation obviously carries through. So 1 by the effective time scale is equal to 1 by tau straight plus 1 by tau parking lot. So these tau straight and tau parking lot are the average times between two successive straight translocations of a single molecule, and similarly this is the average time between two successive parking lot translocations of the same molecule. Now, so they are actually related in a way which is similar to parallel electrical resistance. So this is nice. So now we will try to see that this tau effective is exactly same as what is related to the waiting time distribution of the molecules inside the layers. So I go back here. So the waiting time is basically the region of time the molecules spend in these layers, and this waiting time is actually broken by these translocations, and these translocations can either be a straight or a parking lot. So now, the average tau effective is exactly the same as the residence time of these molecules in these layers. Okay. So that is good. The next thing which we wanted to check is this mean square displacement. So what we did was that we plotted the mean square displacement computed explicitly from the simulations, which is given by these black circles over here. And on top of that, we put this what comes from the continuous time random walk analysis. So we put this n total of t times for each jump the molecule translocates by Smectic layer spacing. So there's a square of Smectic layer spacing over here. So this now has this form of t by tau effective or tau res into L Smectic square, and from that you can see that this red curve actually falls exactly on top of this computed mean square displacement. So there is no fitting here, it exactly coincides with it. So says that this continuous time random walk is working pretty well. So now you can also look into the distribution of these number of jumps. So what is the distribution of the number of these jumps in a given time interval t? So for an exponential waiting time distribution, which is given here, you can explicitly show that this distribution of number of jumps p n total t is a Poisson. So now we have this estimate of this tau t tau res, and for a Poisson process, we know that p n total of t follows this form. So that is shown in this plot. So this p n total of t is plotted for n total for several times, 1, 50, 100, and 200 nanoseconds. And there the black line is what one computes explicitly from the MD, the distribution of number of jumps, and the red dots are what computed from this continuous or Poisson distribution. Okay, so let me sort of say the Poisson distribution expresses this probability of a given number of events occurring in this interval of time. If these events occur with this known average rate, and this average rate over here is this tau residence time, and these should occur independently of the time since the last. So for this case, the dynamics is completely Poisson. Okay, so now let's go and see how further we can go with this sort of continuous time random walk description. The next what we will try to see is we actually would like to compute this g of zt, which is the Vanneau function for the out of plane direction. And for systems which exhibit continuous time random walk, there is this sort of closed expression. It says that the probability that the molecule would end up at position z at time t, given that it was at z equal to 0 at time t equal to 0, is a sort of product of two things. So one is this we have already encountered, this n total t, which is this Poisson distribution, and another is this function that the molecule ends up at coordinate z after n total jumps. So now there are, for this system, there are also analytical ways of, probably analytical ways of calculating this thing, but for this particular problem, I have actually computed this also directly from the simulations. And so this actually now is shown in here, this quantity. So this, the probability to have a displacement z as a function of the number of jumps. So if you don't have any jump, so the molecule is just sitting in its original layer and sort of vibrating. So then you actually see a Gaussian or centered about the origin. And if you have one jump, so you can either jump to the next layer or the layer in front or the layer in back. So this results in these two peaks. So this here, the z is actually divided off by the layer spacing. So it appears at 1, plus minus 1. And similarly, for if it should suffer two jumps, so it can either be one forward and one backward, which results in this peak at 0, or it can go 2 steps front, or it can go 2 steps back. So similarly for the 3 jump. Anyway, so now if you compute all these things and plug these things into the equation, you can actually see that this is a comparison of this GS of ZT computed from the MD simulations, which is shown this black curve here, and the continuous time random walk approach, which is shown by this red circles over here for various types. You see that this continuous time random, this is not again a fitting, this is completely just two calculations put on top of each other. And you can see that this continuous time random walk approach can actually explain all the details of this thing. So initially the molecules are sort of centered in this its initial layer. As time goes on, it starts migrating to these first and second layers, nearest neighbor layers. And with time, this sort of broadens. So this actually says that this continuous time random walk is working pretty much well for this sort of system. So that brings me to the next part of the talk, which is sort of understanding molecular rotation in hydrogen bonded fluids. Okay, so here again, so these molecular rotations actually result as due to hydrogen bond coordination fluctuations. So typical process is shown over here. So this molecule is initially hydrogen bonded to this first neighbor, which is OA, and the hydrogen bond coordination of this OA increases, and simultaneously this OB decreases due to thermal fluctuations. As a result, this molecule breaks this hydrogen bond and rotates and forms a hydrogen bond with this under-coordinated OB, and this OA is left to form hydrogen bond with other molecules. So So here we actually track these basic dynamical events by tracking the sort of changes in the hydrogen bonding partners. So we make a time series of, for each molecule we compute a time series of which molecule it is hydrogen bonded to, and when there are these discontinuities in this time series, that actually signifies that it breaks a hydrogen bond with one of these partners and forms with another. So for this thing, you can again compute the residence time and the jump time again. So so this is a cartoon of this typical plot of this thing. So here what is shown, this baseline is actually the time of the residence time where it's actually hydrogen bonded to one of these hydrogens, and these blips are actually correspond to this jump, orientational jump, where it's actually changing these partners. So again, for these systems, this tau jump is much lesser, much less, at least 10 times less than the average waiting times. And there is another time scale over here, which is this persistence time, which is statistically different from the residence time, but I will come to that distinction slightly later anyway. So this universal mechanism is also seen for supercooled water. We have also studied this similar thing for confined water in nanotubes. And now I've seen it for aqueous binary mixtures, liquid acetamide, eutectic mixture, and ionic liquid. So this mechanism is pretty robust, this angular jump associated with partner exchange. So the typical waiting time distributions are exponential or multi-exponentials in these cases, and the jump length distribution actually looks like this. So this is the jump angles. Here it's the jump angle as function of the angle. So these jumps can be as high as around 60 degrees or more. For water, it's around 60 degrees. For other liquids, it can be 80 to 90 degrees. Yeah. These are between 300 and 250 Kelvin. Yeah. So a large part of, so again, so this also tells you another important thing of these mechanisms, which is again universal for all these types of hydrogen bonded liquids, is that the coupling between the local rotational and translational degrees of freedom. So the initial hydrogen bonded neighbor actually breaks the hydrogen bond and moves to the second solvation shell. And simultaneously, the final hydrogen bonding neighbor moves in from the second to the first solvation shell, and these changes actually coincide exactly with when this angle turns. So this again underlines the microscopic rotation translation coupling in these systems. Similar things now we have been able to observe for these deep eutectic mixtures. So these are mixtures of one or several compounds that form liquid at temperatures which are much lower than their individual melting points. And they show these characteristics of these supercooled liquids in the sense that if you compute their orientational correlation function, they are sort of stretched exponentials. So this is a typical cartoon of these angular jump processes. So you have these mixtures of these acetamide and some salts, lithium salts. So here in this this panel, it's shown that this acetamide breaks hydrogen bond with one of its initial acetamide partners and forms a final hydrogen bond with another acetamide. And here the transition is between one acetamide to a final ion. This is a bromine ion. So these are sort of common and universal features of these hydrogen bonded liquids. So you can see again the microscopic rotational translation coupling even for these systems. And here the waiting times are sort of power law, because these are systems which show this very stretched exponential slow dynamics and those things. So here these systems exhibit power law waiting time distributions. So another system, I'm now coming towards the end. So another system which has a similar characteristics is a binary mixture of water and DME. So DME is a short polymer, and we were able to actually show that in this recent paper there were some terahertz experiments which measures the rotation of these molecules, rotation of water in the mixture of these DME and water. So this DME is soluble in water over the whole concentration range, and there also we could find that these water molecules undergo these orientational jumps, and we could actually sort of semi-quantitatively relate the dependence of the time scales, rotation time scales as a function of concentration, which was observed in these experiments with our molecular dynamic simulations of these binary mixtures. Again, for these systems, if you plot the average number of orientational jumps as function of time, they are sort of linear in time at long times with a characteristic time scale which is related to the waiting time distribution. Okay, so now here I will talk a little bit about supercooled water. So here again we have done the same thing. So this is simulations between 300 and 250 Kelvin. So this is the n of t, so the average number of jumps as function of time. So as you supercool this water, you see the dynamics becoming slower, and this n of t is linear in time at long time scales. Anyway, so what happens if you actually compute the rotational Vanno function? So for that, the MD is sort of this black curve, and from the rotational mean square displacement, you can estimate the rotational diffusion constant. With that diffusion constant, you can plot a Gaussian, and you can see a significant deviation between this Gaussian form of Vanno function and what is actually computed from the mean square displacement. Now over here, so I will come to this point. So here we also computed the mean persistence time and the waiting time. So I would like to define the mean persistence time over here. So you are actually tracking these the time scales at which these molecules are undergoing these rotational jumps. And for that, you actually have an arbitrary starting time, arbitrary t equal to 0 when you start observing. So that is an arbitrary time. The persistence time is actually defined for the time from which where you start your clock to the first jump. So that is statistically different from the distribution of time intervals between two jumps, and this difference is small at high temperatures. In equilibrium, at high temperatures, this difference is small. So what I plot here is the mean persistence time and the mean waiting time. So the black dot is the mean persistence time, and this red one is the mean waiting time. So at around 300 Kelvin, they are sort of close to each other, and as you approach supercooled temperature around 250, so these two timescales starts decoupling. So similar types of observation have been also seen in this set of these kinetically constrained models of these amorphous liquids. Anyway, so for this thing, what happens here? I'm coming to the end of it. So now I'll sort of try to connect with this heterogeneity or measures of heterogeneity. So this is important. So this single molecule rotational diffusivity is now proportional to the number of rotational jumps. So now I am actually computing the probability of P of NT and see how it is behaving at several temperatures. So now this P of NT is sort of Poissonian at high temperatures. This is 300 Kelvin temperatures. At P of NT as function of n is shown at various times. So, and on top of that, this Poissonian is plotted. So it agrees pretty much well. But as you come down to lower temperatures, this P of NT starts significantly deviating from a Poissonian. So this again is attributed to the presence of facilitated dynamics, where again in facilitated dynamics, the distribution of number of jumps is not again Poisson. Another thing is that, so this is again for this binary mixture, so which has a high amount of heterogeneity. Here again, this what I am plotting is this P of NT, and it actually deviates significantly from the Poissonian. So that is beyond the point. Here, what I want to concentrate. So suppose you look at one of these snapshots at around say t equal to 10 picoseconds, and now try to see this P of NT. So this has a huge peak over here. So these are all sort of normalized things. So around 6 to 7% of the molecules have not undergone any rotational jumps at these time scales. Whereas it's sort of coexisting with a group of molecules around 4 to 5%, which has within the same time scale has undergone around 20 to 25 rotational jumps. So you can see this coexistence of these immobile and mobile particles from this distribution of the P of NT. And now this should be actually be compared to the diffusivity distribution, which should be obtained via deconvoluting the Vanno function. This has already been done by Mukherjee and in this JChemistry paper. So this we are trying to do this. So this is also again gives you a nice description of the heterogeneity, where it actually shows a transient bimodality. This transient bimodality will go away if you go to longer time intervals, but this exists for these sort of time intervals 10, 15, 20 picoseconds. Okay, so with that, I will not probably discuss this, and so I'll come to my conclusions and future directions. So this, it seems that the single molecule translational rotational dynamics can be understood as a continuous time random walk. So this has similarity with models of exhibiting facilitated dynamics. So I am trying to explore this further. And another important problem, which is actually finding a microscopic measure of this translational rotation coupling, which I'm trying to do, is that, so the basic idea behind this is that for the same system, say for the same liquid water or the liquid crystal, for the same system, you try to build a continuous time random walk for the rotations and also for the translations, and then try to see how many of these translations actually contribute significantly to the rotation. So that is sort of a near to long term project which I am trying to do, and I would like to thank DST for funding of this project, and these are references, and I would like to thank you for
questions. So I could not understand. Oh.
Yeah.
So are there any examples where the waiting time is power law tail and you?
Yeah, it has. I actually showed you for these glassy deputed systems. It has a power law. Yeah. For the Smectic, no. For the Smectic, it's exponential.
It's always exponential, is it? So there are no examples where you get subdiffusion.
No. At the later times you always get a diffusion, t to the 1.
For the water, you showed for the rotational degrees of freedom, the GS, the Van Hove function, which looked some sort of boring in the sense it didn't have any feature, no peaks, no nothing. And so, isn't this in contrast? I was surprised about this.
Yes. Yeah. So you can see, so there is one catch. So this has been actually computed by so if you talk about these rotational degrees of freedom, they typically live on the sphere. So they are periodic. So, but this has been computed by sort of unwrapping them. So you actually unwrap them so that you can compute long time diffusion coefficients from those things.
That's fine, but so you did not take that into account basically because a lot of the thing is just spinning, which is boring.
Yeah.
The interesting thing is if you go off axis.
No, but for the same thing, if you actually can compute this Vanno function for the orientational coordinates where you do not unwrap this coordinate, there you will you see features like this where you have another peak at some angle. Yeah, so that is what you are asking. Yeah.
What would be the qualitative difference?
Same calculation at higher temperature.
What will happen? What would be the qualitative?
Qualitative difference would be essentially for the waiting time distribution. As you supercool it, there are these two time scales, so it's a bi-exponential arises. So this, if you do it at higher temperatures, you will essentially get a single exponential. and you will recover this Poissonian statistics.
Would it be like the slow dynamics that is occurring in the supercooled state that is sort of encoded in this bimodal structure?
Yeah, in a sense, yeah. Yeah.
So one thing which I wanted to know is the difference between the T persist and the T residence, because the T persist would depend on almost when you start the clock. Right?
When you start the clock, yeah.
But then, so then isn't it a better statistics to just say, okay, after one jump, and then wait for the first thing in that super system? So what is the difference?
Yeah, so the difference is that there is a, yeah, so this point is arbitrary. That point is arbitrary. And actually there's a Feller relation which relates these two time scales. So yeah, so these two distributions are different, but they are related. They are related, and the difference is less if you have higher temperatures, and go to supercooled temperatures, they start different.
Any further questions? Okay, if not, then let's thank both the speakers and Biswaroop for this wonderful talk. Thank you.